So a very warm welcome to all of you on this session of sample size calculation. That is, initially we'll start with the cross-sectional study. And thank you, Venkatesh. And I would like to extend my thanks to our head of the department, Dr. CM Singh, who is always there with us in any of the platform, wherever we want to make a, some significant impact. And in this sample size estimation, we definitely want all of you people to feel empowered so that you are not hesitant whenever this concept of sample size comes. Because as a medical students, it's not necessary that all of us are medical students, but largely I think most of us are related to health in one or the other way. So we, because this is entirely a statistics concept, so we are, as a medical student, we are always apprehensive of calculating the sample size. So we would like to make this journey a little bit hassle-free to all of you, so that at the end of the session, you should feel confident that you can handle this issue of sample size. And I would like to thank Clearnet also to provide this support. So without any further delay, I'll start sharing my screen. In this webinar, we will also anticipate and we will hope that you people also do the sample size calculation simultaneously. So the structuring of this webinar is something like that, that initially with every example, I will show and I will demonstrate it. And then 1 or 2 examples you have to do on your mobile or a system. So I hope that all of you are on either laptop, at least, because we will be doing a calculation using an online calculator, and unless and until you do it, you will not learn it. So simultaneously, whatever exercise we give you, kindly answer it in the chat box. And there are Zoom poll sessions also, so do answer those questions, because then at the end of 90 minutes, you will have some take-home message so that you can use all those concepts whenever you plan any research. So I'll start sharing my screen. So today's session is entirely on cross-sectional study design. So as I've already said, that the aim of this webinar is to make you people empowered to handle this issue of sample size calculation in the cross-sectional, and then in the next sessions, we'll see about the case control, cohort, randomized control trial, etc. So now this question is to you, why you think that sample size calculation should be done, or why there is so much whenever you go for any presentation, whether it is a IC, whether it is a IRC. IC stands for Institute Ethical Committee or Research Committee, or any proposal, whether you submit your proposal in ICMR or any other funding agency, there is always this issue of sample size calculation. Now, this question is to you, that in a medical college, you randomly select 5 students, and that medical college could be any medical college, like you can imagine your medical college, and you have been asked whether the refractive error is there or not. So out of 5 students, you have seen that 3 out of 5 students have said yes to this question. So the proportion is 60%. So can you say that the 60% of the students in that medical college has refractive error? So the option is only yes or no. So like you can, most of you are answering it as a no. So yes, you are right that we cannot say that only by examining the 5 students. Now see this question. In your hospital labor room, you randomly select newborn, and they recorded their birth weight as 2.6 kg. And then you have to say whether they are what is the average birth weight. So that birth weight is 2.6 kg, 2.4 and 4 kg. So can you interpret that the average birth weight of your hospital is 3 kg? So yes, I should expect more. There are few answers like yes, and like there are more, most of the answers are in no. So only by selecting 3 newborn and calculating their mean, it will not convey that the birth weight of the babies are 3 kg, mean birth weight. Now see this third question. Again, the option is yes or no. So you check the OPD registration file for the year 2020 and you randomly selected 5 days and you looked for those OPD numbers. It was 200, 300, 250, 50 and 200, any 5 days. So can you interpret that the average OPD registration per day is 200 in your hospital for the year 2020? Can you say something of this sort? So yes, most of the participants, yes, there are few yes too, but I think most of you are saying that it is no. So the people, those of you who have answered no, you are right. Because out of 365 days, that person has selected only 5 days. And the average of 5 days cannot be taken as a mean of the entire year. So that's the point. And Dr. C.M. Singh in his welcome speech, he has said about the generalizability. We will talk more about this generalizability later in this session, but definitely all of you are very clear that only by saying that average of 5 days we cannot be very certain that, mean of the entire 365 days will be 200. So now reconsider these same questions, but here the answers are yes, no, and maybe. So now in this case, the same question. In the medical college, you have randomly selected, there you have selected 5, but now you have selected 50 students and you asked whether they have the refractive error or not. And out of 50, 30 said yes. So now can you say that the 60% of the medical students are having refractive error? So there are 3 options: yes, no, and maybe. So like most of you are either answering yes or answering maybe. Okay. Now see the second question. In the second question, in the hospital labor room, you selected 30 newborns and then recorded their birth weight and you calculated that average as 3 kg. So can you interpret that the average weight of the hospital is 3 kg? So maybe. Again, your answer is maybe. Now, this is the third question. You check the OPD registration file for the year 2020 and you randomly selected 50 days. And now you are saying that the average, based on those 50 days, you calculated the average as 200. And now you are interpreting that the average OPD registration per day is 200 in your hospital for that year. So answer is maybe. Yes, most of you are answering maybe, or there were few no's also, but the correct answer would be either yes or maybe, because we don't know sample size. Still, again, the same questions you have to answer once more. So in this case also, you have got only 2 options and those 2 options are either yes or no. So again, from that college, you have selected 500 students. And then out of those 300, 50 said yes. So now can you say that the 60% of the students at that medical college has refractive error? So what will be your answer? It will be, by mistake, it has written 500. You have randomly selected 300 and 50 out of 300 has said that it is refractive error. Similarly, you have selected 300 newborn and recorded their birth weight. So now can you say that the calculated average weight is, in this case, sorry, so calculated average weight is 3 kg. So what will your answer? So again, your answer will be so now you can see it depends on the total deliveries. Yes, you are right. And you can see here that obviously you need a sampling frame. Like many of you have raised this question that how do you know that whether this 300 is adequate or not? But one thing is sure, as you move from left to right, in this case, like let us see this example once more, that you check the OPD registration file for the year 2020 and then randomly selected 150 days. So out of 365 days, 160 days, 150 days are there. And now can you say that the average OPD registration per day is 200 in your hospital for that particular year 2020? So yes, you can say that, because this 200, that represents this 150 days, that represents the 365 days. So in all these example, you have seen that certainty, it has from no, your answers turned out to be maybe, and then it was yes. So as we increase the sample size, the level of certainty with which we can say about the population mean or the population parameter, the certainty increases. And that's the beauty, or we can say that's the importance of sample size calculation, because the sample, why we are ultimately doing the research. So our ultimate aim of the research is to project, or is to convey about a population parameter, because population parameter is not known. And through the samples, because you are withdrawing various samples from that population, and through that sample, you want to project the population parameter. So ultimate aim is to project population parameter. And as you increase your sample size, this level of certainty, it becomes more in projecting or in saying about that population parameter. So now, can you decide this number arbitrarily? Can any arbitrary number be a sample size? Like in many of the studies, and in many, especially the clinical side, people say that, they will perform on roughly 100 number of individual. Maybe somebody's, if that 50 looks good to him, so he will perform in the 50 number of people, or 75, 100, 200, or so on. Or maybe many people, they calculate or they project their population parameter in sample size as low as 16, 18, 20. So can there be any arbitrary number to say that? So answer is definitely no. It cannot be any arbitrary number. Rather, it is based on many assumptions and many set parameters, which we will see about those parameters. So now there are two sides of the same coin. Either you can have a very small sample, or why to calculate the sample? You can take the whole, study subjects. If it is a OPD, or if it is a, a small clinic, then you can take all the people, all the patients or the clients who are coming to the clinic. So either there can be the deviations from our adequate sample size could be either the sample size, one case is the sample size is very less, and the other scenario can be that the sample size is very, very large. So what is the problem with this small sample? If your sample size is small, like if the required sample size is maybe 250, and you have conducted your research on maybe 120, then the clinically significant difference also, it will be clinically and statistically significant difference will be seen as statistically insignificant. So then you will not find anything. And you will say that, see, in my study, I have not, the previous studies, they have found out that, but I'm not able to find that. Maybe small sample size could be one of the reasons for that. There are other reasons as well, but with a small sample size, the clinically significant difference, it may declare as a statistically insignificant. Although you can still say that, you think that, you in limitations, you can mention about your sample size that these were the limitation. But again, that population parameter, which you are saying, which you are conveying, that will not be a very precise. So the external generalizability of your research will be compromised. Now, this is the problem with the small sample. Now coming to the large sample. If you've got very large sample, but there may be a researcher who will say, why to bother about all the sample size? I'll take everyone who is coming to me. Let's do it. But what is the problem with a very large sample? Apart from, there are problems like feasibility and budget also, because budget is limited, time is limited, resources are limited. But still, if you think that, no, I have all resources, I have all time, and I'll include all those study subjects who is coming to me. So what what problem may arise with a large sample size. So a large sample size, again, it has got a problem. It may declare a clinically insignificant difference as a statistically significant. We will see it. Because if you increase the sample size, even a very small clinical difference of 4 or 5, it will be very statistically highly significant. No confidence interval will be, it will not have 0 or 1, or the p-value will be 0.001. So you will convey ultimately that it is highly statistically significant. But if you think and ponder about the clinical significance, you will not be able to justify it. So that's a problem with a very large sample size. That's why you should have an adequate sample size in your study subjects, so that the this clinically this difference you can appreciate. Now, what is this clinically insignificant? That we will see in the next example. So now again, there is a concept of law of diminishing return. So in the law of diminishing return, if you increase the sample size after certain level, it starts getting saturated. Means that the parameter or the estimate which you are measuring, it will have no impact. So that is known as the law of diminishing return, because whatever you are putting, that extra person or that extra study subject, it is not going you to give return, because already your result, your confidence interval, it has saturated. So it may not offer any statistical benefit to you. So now there are few responses. So please submit those responses in the Zoom poll. So the question was, you recorded hemoglobin level of 5 children of a village X, and the average calculated was 11 gram per deciliter. And you want to generalize your finding to all children of village, but due to small sample size, this finding may be a underestimation, overestimation, or both. So yes, answer will be both. As anything can happen. You don't know whether the 5 children which you have taken, they belong to a category of good hemoglobin, or they belong to a category of a poor hemoglobin level. So it can be underestimation or it can be a overestimation. Yes, rightly said by many people.
So ma'am, I'm stop the sharing for this poll and sharing result.
Okay. So this was so now coming to the concept of generalizability, we'll answer all the questions at the end. We are noting down all the questions, right, regarding this clinical significance and insignificance also. So we are noting down all the questions and we'll answer to all those questions at the end. So now let's come to the concept of generalizability. So the concept of generalizability, for that, let's understand few concepts of the research question. So the research question has 5 components. Many of you know this also. It is denoted by the mnemonic PICOT, where P stands for population, I stands for intervention, C stands for comparative group, O stands for outcome, and T stands for time. So let's find out P from the following questions, because we want to know about this population about which we want to infer our result, about which we want to project our result. That's why the knowledge and the concept of population, it is very important. So now let's see, and you have to type in the chat box regarding the population in the following research question. So now this question, this is the research question. Is there any difference in serum ascitic fluid albumin gradient and ascitic fluid protein in hepatic and non-hepatic causes of ascites. So what is the study population here? Please type in the chat box. So yes, you're right. They are patients, but the more specific would be the patients of ascites. And then when later we can classify them as the hepatic and non-hepatic causes, but the population is patients with ascites. Very right. Now see the next question. What is the incidence and risk factors for deep venous thrombosis in medical intensive care unit? Please type the population in the chat box. Yes, ICU patients. MICU patients, patients in, yes. So you are right. It is the ICU patients. More specifically, you can write medical ICU patients, but definitely these are the ICU patients. So your study population is ICU patients. And then only whatever the result will come, you will be able to generalize that result to that particular population from where you have drawn your sample. So you have to be very careful regarding this population, whatever population you defined, from where you are withdrawing your sample. Now, the third question, is there any derangement in the pulmonary function test and absolute eosinophil count of male workers in petrol pump? So yes, answer is right, male workers in petrol pump. So like there's one research question where you want to know the proportion of diabetic patients, what proportion of diabetic patients is having a diabetic retinopathy. So can you include all the diabetic patients in your study? Answer yes or no. You have to keep on typing. Otherwise, I'll not be able to know whether you are listening or not. So yes, no or yes, mixed response is coming, no or yes. So the correct answer is, well, the answer depends on the size of the population. If the size of population is small, and if you can include all of them, then obviously you can. But if the size of population is very large, then is it feasible for you to include all those diabetic patients? So it depends. But usually we don't carry out a study on whole population. Even if your clinic, you are the person who is looking after the clinic, or you are sitting in a OPD, it is not only who is seeing the patients. There are many other residents, there are many, it's a teamwork. So everyone is seeing the patients. So it is not usually possible to include each and everyone in your study population. That's why you take a sample. So then how to know about the parameter? So that's what we discussed in the beginning, that why we are doing a research. We are doing a research because we want to project, or we want to estimate the population parameter. So that prevalence of diabetes, blood sugar, how we are going to know about that. So that's why you need to select a sample which is the representative of the population. So that sampling error, because if that sample is not representative, you are introducing a sampling error, and that error will impact your outcome, and it may have a less or more effect than the usual. So this representative portion is known as the sample. So now just see this example. This is a population where you can see the green and the orange. So orange is women and green are men. So you have selected from this population, you have selected a sample. And on that sample, you have calculated the statistics. So that sample, whatever you calculate, that is known as the statistics. And what you generalize, it is known as the parameters. So you estimate those parameters and you generalize it for the population. And you can, but there is one very cautionary line. You should generalize your finding only on that population from where you have withdrawn your sample. You cannot generalize your finding from those sample who were not a part, or from that population who were not a part of your study. So you should be very cautious regarding external generalizability of your result. Your study findings are applicable only to that population from where you have withdrawn the sample. So that's how the concept of sampling comes, which we are not going to deal in this session. We are only focusing on the size. How you select those samples from that population, that is an entire separate session. So this session will focuses only on the number, size, calculation of sample size. So like in this case, if your study population, and if you are withdrawing a sample from the MBBS 202 batch of AIIMS Delhi, then your result will be applicable only to the 202 batch of AIIMS Delhi. If you are recruiting individual from all the medical colleges of 202 batch, then this will be a MBBS 202 batch of Delhi. Similarly, if you are recruiting diabetic cases of a XYZ hospital, then your result or your generalization will be diabetic cases to that hospital only. You cannot generalize it to the all diabetic patients. So that's how by all these examples, we want to convey this to you, that whenever you generalize this finding, your generalization should be only to that population from where you have selected your sample. And again, like if you are doing some study on pathological specimen of XYZ hospital, then that result will be applicable to only the pathological specimen received in that particular hospital. So now let's revise some basics of the cross-sectional study. So like all of you know, any research design, you classify it as a observational and as a experimental. And under observational, you have a descriptive and analytical, and in descriptive, you have this. So I'm not going into that experimental thing. If you see on the descriptive and analytical, so the cross-sectional comes in both the thing. There is a descriptive cross-sectional, the classical surveys which we do, that is a form of a descriptive cross-sectional. And there is an analytical cross-sectional also, where we do the hypothesis testing. So whenever you go and measure the outcome and the risk factor simultaneously in one snapshot, we call it as a analytical cross-sectional. So in analytical cross-sectional, you select the sample from a population and you determine all the variables only one and at same point of time. And then you see the association. The population can be a hospital records. It can be a 5 X-ray plates. It can be a pathological specimen. It can be a blood specimen too. So depending on the setting where you are carrying this study, the population can be anything. By the term population, don't think that it is a, it is a live study subject. Your population can be anything. Then steps in sample. Now coming to the steps in sample size calculation. So in this sample size calculations, there are basically few steps which are involved. If you go in that step, everything is very organized and then you can interpret it very scientifically. So the first step is you should identify the outcome or the major study variable of your research question or from your objective. So in your any research design or any research question, there are 3, 4, 5 variables, major variables. But out of that, which is the most important for you, you should identify that variable. And then again, you should classify its type. Because sample size calculation, we'll see, we classify it based on the mean or based on the proportion. So that classify whether it is a continuous variable or whether it is a categorical variable. So that we identify according to that. And then based on that, we do the thorough literature review. Why we do the thorough literature review? Because we want to have an estimate from the previous studies. That we will see how to do it. The next step is to set the parameters for the sample size calculation. So that parameter is basically about your assumptions. At what confidence level, at what margin of error you are setting your parameters, or at what level, whether it is absolute precision or relative precision, that we'll see. Everything we'll see one by one. And then the fourth is you have to calculate the sample size. After calculating the sample size, you have to make adjustments. because you have to either adjust it based on the finite population, or if there is a clustering of your samples, you have to put a concept of design effect, or you have to adjust based on the response rate. So this adjustment we do once we calculate the sample size, and then we do the write-up. So after we have come up with the sample size, we write in the under the section of sample size calculation that what are the assumptions with which we have calculated this sample size. So these are the 6 steps involved in a sample size calculation. You have to identify the major variable, then you have to do a thorough literature review to get the set parameters. Then you have to have some parameters, like depending on your analytical cross-sectional or a descriptive cross-sectional, about the value of alpha, precision, and etc. Then calculate the sample size, do the adjustment, and then do the write-up. We will see each step one by one. So the first step is identify the major variable in your study or research question. So like in this case, you can see there are many variables which you can see on the screen, like the pain status, obesity, vitamin D status, exam result. So if you want your outcome to be in the form of mean, like mean VAS score, VAS is the visual analog score, scale score. Then if you want to have a BMI, you want to show it in the form of mean BMI or vitamin D level or mean marks. So if mean of all these forms are there, then it will be a continuous variable. But if you want to have a categorical nature of these variable, if you divide this VAS score in mild, moderate, and severe, or if you divide this obesity into maybe present or absent, or maybe overweight and obese, depending on criteria, whichever you take. And again, the serum vitamin D level also, like you can classify it like normal and deficit. Exam result also you can classify as a pass or fail. So you can see in all these examples, you are converting a continuous variable into a categorical variable. So your sample size, the first step is you have to identify a major variable, whether you want your variable to in the form of a mean or a continuous variable, or you want your main study variable in the form of a proportion. That's the first step. Now it's the time for Zoom poll. So you have to answer that. So answer this question. So study variable is gender. Only mean possible, both possible, only proportion possible. So you can see that 78 out of 139, we had to stop because the time is less. So I'm sorry for that. Only proportion is possible out of 56% have answered this. But both possible, the 35% of the participants out of the total 139, you have answered both possible also. But this gender, there cannot be a mean value of this gender, because gender is always categorical. Either you will be male, you can be categorized as male or female or some other, maybe there are other genders also. But it cannot be some mean value. You cannot take the mean of 1 or 2, or if you give a categorical value to it. So the correct answer would be only proportion. There are few variables which can only be defined as a categorical variable, and gender is such type of variable which can never be a continuous variable. So only proportion is possible in this case. This is another question. So the study variable is blood loss. Now, so now you can see that out of I think only proportion is 10%, but majority of you have answered it as 63%. So you are right that blood loss, you can define it as a mean, how much of loss is there as a mean also, or you can categorize also like mild, moderate or severe. So you can have some category that up till, 200 ml it is mild, or 500 it is moderate, and more than that it is severe. So you can have a both sort of category in this case. Now coming to the next. So I think this was the last question. So we'll go ahead. So now you must have observed in this case. Just a second. So the categorical variable, only proportion is possible. For a continuous variable, both mean and proportion is possible, because if it is a continuous variable, anytime you can take any cutoff and you can convert these continuous variable as a categorical variable. So that was the first step which we discussed. Now the second step was the review of literature. Now why do we do review of literature? So basically we do the review of literature and try to find the similar study which has been done already on our research question, because then we will be able to identify what was the outcome in that particular study, based on which we can calculate the sample size. If you do not, if your study is so naive and novice, and you don't, you are not able to find exactly similar study, then you can do a pilot study, maybe on 15-20 cases, and then you can have some estimate. And based on that estimate, you can calculate the sample size. Even that pilot study is also not possible, then you can have a best guess, or with your experience of your guide or your mentor or your senior, you can put that sample size criteria. But in all these cases, you have to mention that what criteria are you using? Are you using any previous already published literature, or are you using the estimate of a pilot study, or you are using a best guess or out of experience, or you think that this should be there? So whatever you decide, you have to mention in your study sample criteria. Now third is you have to set the parameters for this. This parameters, basically now the concept of alpha and beta error comes. Many of you are familiar with these concepts, but still I will revise those concepts once again. So in these parameters, the definition of alpha error and beta error, this is true for a hypothesis testing. So whenever you are planning for a analytical cross-sectional, where you are going to have a hypothesis, a null and an alternate hypothesis, then you should use this. So in this case, null hypothesis always says that there is no difference between the two groups. Like in this case, if my hypothesis is like mortality due to COVID, if I say that it is higher in males as compared to females, so what I'll do, I'll compare the mortality in males and I'll compare the mortality in female, and I'm saying that mortality is high in female. So the null hypothesis would be that there is no difference. And because we don't know the reality, what is happening in the real, because that database, all over world database, we don't have. There, if you can imagine a hypothetical situation where the all over world data is there with us, all the COVID patients. And if we analyze this mortality in male and female, then definitely there is no point of this hypothesis testing, because we have included each and every one who has suffered from COVID and maybe who has met with this mortality. But since we always, like we have talked regarding the sample, we are always projecting the estimate of our sample to that population. So that's why in reality, we don't know what is there, but hypothesis, the null hypothesis is that there is no difference. And if we have also concluded that that is the right decision, and we have concluded that yes, there was a difference, and actually also there was a difference, then also we made a right decision. But the problem arises, there can be a possibility that null hypothesis was true, but we have rejected it. So that will be your alpha error or type 1 error. Or the other possibility is null hypothesis was false, but we have accepted it. So that is the type 2 error or beta error. So this is the concept of type 1 and type 2 error. And that's why we fix these error while calculating the sample size. So we fix this error of alpha error at least up to 5%. And below that you can take, but in my study, I don't want whatever sample I draw, I don't want the result of my study to give the type 1 error more than 5%. And what is that type 1 error? That actually there was no difference, but I have said that yes, there is a difference. This was basically the alpha error. Similarly, the other concept is of power. So this type 2 error, if you 1 minus beta is the power of the study. So what is the power? Power is basically the difference which you are suggesting. How much power your study has to detect that difference. Because ultimately, what are you doing? You are saying that beta error is 20%. So beta error 20% is that in only 20% of the cases, you are allowing that actually there was a difference, but by mistake, you said that there is no difference. So most commonly parameter which we set for calculating sample size is either 5% alpha error or 1%, depending on your study, whatever you want to take. It depends entirely on the researcher. Similarly, type 2 error is entirely on researcher. You can take the 20% or 15% or 10%. So I will once again repeat the concept of power. So basically power is what? Power is detected, that ability of your study to detect the difference. Power, the concept of power is only applicable to hypothesis testing. Like in this case, if I say that the mortality in female is 10% less than the male, that I have said that mortality in female is 10% less than the males, then if I set that power 80%, that means the power of my study of that detecting difference is 80%. That means there will be only 20% chances that I am wrong. Means there is a difference. Obviously, if there is a 10% mortality, that means there is a difference. But there are only 20% chances that actually this difference was not existing. So in 80% of cases, in 80%, this will detect the power. That means that 10% difference, which I'm projecting, that the mortality in men are 10% higher than the women. So that 10% difference, your sample size should be large enough to detect that much difference. And that's why we say the power of the study. So the minimum acceptable power is 80%. You cannot have a power less than 80% because then it is not justifiable. Yes, you can increase your power. You can make your power like 90%, 95%. We will see in the calculation of sample size, when we will see the statistical calculation, that many of the researchers, they put their power as 90%, as 95%. As you increase your power, your sample size increases because you need more sample to have that powerful detection of difference which you are proposing in your study. Similarly, the less alpha you have, the sample size increases. That we will see. If you have 5% alpha error and if you have 1% alpha error, then the sample size in 1% alpha error will be much more than the 5%. So as you decrease the type 1 error, your sample size increases. As you increase the power of the study, your sample size increases. Okay, so I'll go Again, these are the most commonly set parameters. So now calculation of the sample size. So the calculation of the sample size, we can use the formula, but these, we don't use these anyways, this formula. You can use the software. There is a EpiInfo, there is a SPSS, R software are there to calculate the sample size. You can use the mobile apps also. There are many mobile apps which we can see. And then you can use the online calculator also. So, but this online calculator, we will show you with this online calculator. We will use this online calculator. Now the next or the fifth step is we have to make the adjustment. So once you have calculated the sample size, you have to adjust your sample size because you have to estimate the population parameter. And to represent your sample up to that particular population, you should adjust your sample size. So basically we do three adjustments. We do the finite population adjustment. We'll see each of these three adjustments one by one. Then we do the design effect. So if you're doing selecting a population, selecting your study subjects at a multi-level stage or multi-stage sampling, then that design effect is there because there is a clustering of your study subjects. So then you put this design effect. Or the third type of adjustment can be based on your response rate. So how much response rate you anticipate or how much loss to follow-up you anticipate. Loss to follow-up concept is there generally in the cohort study. But this response rate is applicable for all type of studies. So depending on the response rate, you adjust your sample size. So adjustment we do with respect to three components: the finite population, the design effect, and the response rate. Now adjustment for finite population. Normally, whatever sample size we calculate, that is done with the assumption of infinite population because you don't have a sampling frame which is available with you. And then you calculate the sample size. But this, if you have got some sampling frame available, like in OPD, if you know that, how much patients you expect, in the last whole 1 year, because if you are doing a study which is going to be there for 1 year, you can take the, database of last 3 years and you can see that how many average number of people reported to that particular clinic in that last 3 years. You can take the mean of that. So you have got some numbers or some sampling frame available. Or if you are doing it record based, maybe that like COVID, many people, they did their study analysis on the already from the COVID database. So if you have got like 1800 patients of COVID in the last 1 year, and if your calculated sample size is many more, then already you have got a sampling frame. So you can do a population correction. So this population correction is needed only when your sample, your defined or the sampling frame is less than 10,000. Because if your sampling frame or the population is 10,000 or more than that, then the sample size estimation, even without doing this finite population, is nearly the same. So now this correction, because this correction reduces the sample size. So that's how you do this adjustment for finite population. But if the sampling frame has only 100 subjects, then we don't recommend you to go for this finite population if you are doing this single proportion, because there is a very less, there's only less number of individual which you will be able to reduce. Otherwise, the calculation of both will be nearly same. Now, the second adjustment which we do, that is for the response rate. So a response rate is basically researcher has to fix that response rate. It can vary from 5% to 20%. So if the response, if you expect that because of something the participant will deny or they will be unavailable, or the records which you anticipate that is not complete or some missing records are there, then this 5 to 20% of non-response you can take in your study. So it is basically a researcher discretion what response rate do you want to take in your study. Now coming to the concept of design effect. So design effect is applicable when you are selecting these subjects or when you are selecting your individual at a cluster level or at a group level, so that you can define that individual belonging to a particular cluster. There are naturally occurring cluster, like there is a village, there may be a hospital. If you want to include all the hospital of your city, and if you want to take patients from that, then hospital will be a cluster. If you want to take school of your area, then that school will be a cluster because you are going to select the individual from the school. So if you are selecting individual from any of these particular cluster, what we call as a cluster, then you have to apply the concept of design effect, because it is not possible to do a simple random sampling. I'm not going into the detail of the type of sampling available to us, but I hope all of you know what is a simple random sampling. When you have got a list of everyone, in that you have got a sampling frame and you have to select individual from that. Whatever sample size comes, you select those individuals from your sampling frame. But most of the time that sampling frame is not available with us. That's why we go for this cluster sampling, where naturally occurring clusters are there and you can pick individual from that particular cluster. So in that case, you should you should adjust your sample size using the design effect. So like in this case, you draw sample from a very large population using simple random technique. But I said that is not possible. So you try to identify the subjects based on the membership of a group or cluster. That's why it is usually done as a multi-stage sampling. So the design effect, it is usually affected by the intra-class correlation coefficient. The intra-class correlation coefficient is the rate of homogeneity in a cluster. So it tells you how the members from a given cluster correlates, how homogeneous they are. And it also depends on the between cluster variation. So there are two variations, within cluster and between cluster. We will deal with these concepts in detail in randomized control trial. I'm just touching this concept here because these options are there in the calculator, which we will show you. So to make myself clear, this design effect we apply wherever we are doing selecting a individual from a cluster. That cluster is usually, it is a naturally occurring cluster, and this ICC or the class correlation value, it is usually not available. So either you can have this from your previous study, or this correlation leads to the less information capture. That's why in a cluster sampling, you should have more individual to have a population estimate of the parameter. So you can set the value of ICC using table. So a value of ICC is like, if your value is less than equal to 0.1, then it is a low ICC. If it is up till 0.2, then it is, you can say it is a medium. And this ICC is the degree of homogeneity, but degree of homogeneity within cluster. And then if it is more than 0.2, then it is a high intra-class correlation coefficient. So if you have got no value, then you can set like this medium value of ICC. You can take up till 0.2, and then you can calculate the sample size if you are using a cluster sampling or if you are doing a multi-stage sampling. And design effect is calculated based on the following formula. So design effect is 1 plus m minus 1 into rho. So rho is again this ICC, which you have seen here. This is the rho. And this you don't need to calculate it actually. When you give this input in the calculator, it automatically calculates it. Just for the purpose of understanding, I'm explaining this. You don't have to do it manually. Please don't worry. All these concepts are only to make you understand the input which we have to give in the sample size calculation. So here the D is the design effect. M is the number of individual per cluster. Like we say the cluster size. Like if you select a cluster, how many individual, like if you select a school, how many students you are going to take from that school, 10, 20, 30, 40. So this is the number of individual per cluster is M, and this rho is the value of ICC. So you can take from the previous literature or you can assume. If you have no information regarding the design effect or ICC, you can take as design effect as 2, because that's the safest option. If you don't have anything, practically for all practical purpose, you can take design effect as 2. But if you are very clear on the number of individual per cluster, or if you are very clear or sure if you have found out this ICC, then you can calculate this design effect. Up to you. So now coming to this, so we have seen the steps. So we have seen all the 6 steps. Now we'll see the sample size calculation in the cross-sectional study design. So before we go to demonstrate, first and most important thing is which formula you should apply. That although we will show you, but we are not doing a manual calculation. We are using this calculation which is there already on a statistical software. And then second is what formula do we need to put, and the third is how to write up, because write up is very important. Many times you will calculate the sample size and you don't know, like PG students and many students, they come and they say that what to write, how to write it, whatever the sample sizes come, because it looks very messy to them. No, all those assumptions, the alpha error, beta error, power, etc. So they get confused what to write. And that's the most challenging part for them whenever they submit any proposal. So we will show you in that software also that write-up is also there. That template is there. You only need to change it little bit based on your study or your research question. So we have divided this whole sample size calculation using the 4 input. First, we will see it with a single proportion. Then we will see a single mean as an outcome. Then we will see if we have got 2 proportion, then how to get a sample size. And then if you have 2 means, then how to get the sample size. So if you are comparing 2 means and 2 proportion, definitely it will be a analytical cross-sectional. And if you are doing a single proportion and single mean, usually it is a descriptive. So now assumptions in case of this single proportion, you should have an expected proportion and that review of literature. If you are doing a thorough review of literature, you will have this expected proportion, or you take it from that review, what is the expected proportion of that particular outcome, and then you define the confidence level and precision. We will see how to do it. In case of a mean, you should have an expected standard deviation, because it's a continuous variable, so you need standard deviation, and the same confidence level and precision is required here also. If you are comparing the 2 proportion, then you should have either the 2 proportion or 1 proportion and the other is the difference or odds ratio. And since I said that it is an analytical cross-sectional study, so you need to have a hypothesis testing. And there comes the importance of alpha level, alpha error, or the beta or the power, which we have talked regarding the type 1, type 2 error. Remember, we talked regarding that hypothesis testing of mortality in men and women. So if you have got 2 proportions in a cross-sectional study, definitely it is a analytical cross-sectional study. And there comes the importance of hypothesis testing. So this hypothesis testing, it never comes in the single proportion and single mean, because there you are estimating, and there it is not an analytical, it is a descriptive. But in analytical, when you have a null hypothesis, when you have alternate hypothesis, then comes the assumption of this alpha and the beta level and power. Similarly, while comparing the 2 means also, you should have either the mean difference and the standard deviation and the alpha level and the power of that, whatever assumptions you have made. And adjustment, we do it for all of them. Adjustment, we have read about the adjustment. We do the adjustment with finite population. We do the adjustment for cluster level sampling regarding the design effect. And then we take the option of non-response rate or the response rate, wherever it is required. It is not always necessary to do the adjustment, but if you feel that you should adjust or your sampling method involves cluster sampling, then definitely you should adjust your sample size. So now starting with the sample size calculation for single proportion. So generally it is a type of descriptive cross-sectional study. So the formula given for the single proportion is given by Cochrane. I'm not going into the detail of the formula. So this Z square P and this 1 minus p divided by d square, where the z is the value at 95% level. We take it, this value is 1.96, or roughly you can take 2. So that's why you must have read about this 4pq by L square. So this is again the same thing. If you take the value of z as 1.96, then it will be 1.96 into, yes, this 4pq by L square is, it's also okay. But generally what we do, we don't have to do it manually. That's what I want to emphasize. You do it in the calculator, because that will give you a write-up also. So this is the value of z at the assumed level of confidence. P is the value of percentage for the parameter, whatever parameter you are estimating. And this D is the assumed percentage for margin of error. So this D, it can be absolute percentage, or we will see the concept of absolute and relative precision. So for single proportion, what all information do you need? You need the level of confidence, you need the expected proportion, and you need the margin of error or precision. So what are these? We will see these, all the three things one by one. These three information is must. Other is maybe, like if you want to have correction or the adjustment of your sample size, if you have got a population frame, then you can do the finite population correction. If you are doing a sampling based on cluster sampling, then you could do this design effect. You could have this design effect. Or if you anticipate that the response rate will be less, then you can adjust your sample size based on response rate. So these three options, these are optional, but the upper three, the yellow one, level of confidence, expected proportion, and margin of error, these are must. So now what is the level of confidence? Level of confidence is basically the, based on any subject, based on any study, you calculate a sample statistics. So now you say that this confidence level is the proportion of all possible samples. Like from a sample, you withdraw many, from a population, you withdraw many samples. And this level of confidence tells you how confident you are that all those samples who have been withdrawn from that particular population will have the population parameter in that interval. So mostly we use the 95% level of confidence. That means we are 95% confident that the margin which we have used, the population parameter will lie between those two margin only. We will see this shortly in an example. Like in this case, you can see this picture. This is a population of 2,000 people, and you wish to estimate the proportion of hypertension in this group. Okay, so this is my research question. So what I did, I took out 200 individuals from this 2,000 population, and at 95% confidence level, I have calculated that 46 out of the 200 people are hypertensive. And I have said that the 95% confidence interval is between 17.5 to 29.2. Okay, so based on this 200 sample, I have projected for these 2,000 population about this confidence interval. Now in the second, there are 5 more researchers. So there's one researcher who has also taken one sample. The second researcher has taken this sample. Third has taken this. So 5 researchers, they have recruited 5 different samples of 200 people or maybe 100 people, depends. So if there are 100 researchers who recruits 200 samples from the same population, then 95% of the sample will have the confidence interval between, or will have the population, that parameter of that hypertension between 17.5 to 29.2. So you can be 95% confident that your parameter, that population value, it will be the same between, it will be within these two range from 17.5 to 29.2. So this was the concept of confidence level. So confidence level, 95% confidence level means that you give the confidence interval and then you 95% confident that the samples, whatever samples you withdraw from that population, they will have the values between those two range. Now coming to the precision of the two concepts of precision, that is the absolute and relative precision. So that absolute or relative precision, it depends on what you want to take. So let's see this concept again with the example. So with absolute precision, there is a concept of percentage point. So now see this example. The cost of this Amul chocolate in 2020 was 20 rupees. And the cost of this Amul chocolate is 15 rupees in 2021. So if you talk about this percentage point, then what is the absolute cost reduction? So it will be 5 rupees. But if I ask you what is the cost percentage relative cost reduction, then it will be 20 rupees minus 15 rupees. That will be the 5 rupees by 20. So it will be 25%. So similar is the concept of absolute precision and relative precision. So absolute precision, if anywhere you read this concept of percentage point, then this percent point, it reflects the absolute because it doesn't take the denominator into account. Whereas this relative precision, it will give you the percentage of that numerator or that outcome variable which you take. So that's the difference between absolute and relative, but you can take either. It is up to you. And in the software which we will show, you have got both the options. Ideally, it is the same. So next, you can see that if the prevalence of diabetes is 20% in this population, if I say that the prevalence of diabetes is 20% with a 3% absolute precision, that means that this is a percentage point, because I will be saying that my population parameter will lie from this 17% to 23%. So I have taken 20% minus, that will be 17%, and 20 plus 3, that is 23%. So this is percentage point. If I say that the prevalence of diabetes is 20% and I will take a 20% relative precision, in this case, what I will do, I'll take 20% of this 20, so it will be 4%. So the precision, relative precision will be 20% plus minus 4%. So it will be from 16% to 24%. So is it okay to all of you? This, so this is relative precision. Now let's do the calculation. So now this is one example which you can see here. This is the indication, the title of the study. So we have taken all the examples from the published literature. So this was one study where the author tried to see the indication and determinants of the cesarean section, a cross-sectional study. So the research objective was to explore the indication of cesarean section along with their socio-demographic and obstetric determinants. So in this case, the selection unit was patients. So the patients, so do you want that concept of absolute and relative precision? Okay. So again, I'll keep on emphasizing about these concepts once we are doing the calc. So I will demonstrate. I'll demonstrate it and then you will be able to appreciate. Okay. So in this case, if you go down, so this was, everyone has read to this, that this is a research objective. I have to calculate the sample size for this study. Okay. So if you see this, so I will demonstrate it. So you just see this colored portion. So this colored proportion is estimated proportion. So this estimated proportion you can see here, this is the prevalence of cesarean delivery, and he has taken this reference 11. So this author has used a published literature to see the value of his outcome variable. So he or she has taken 49.62. So that is the proportion, and margin of error he has taken as 0.05. So 5% he has converted into decimal and it is 0.05. And then you can see the N. So the estimated population size, he has written that the pregnant female attending the hospital during the study period is 245. So he has given the finite population. And then he has written the 95% confidence interval, power, and all. Okay. So we will see again all these. So this is a sort of descriptive, because he's only doing the, if you see the research question, this patient selection unit is patient. He's not selecting the hospital. And here he's mentioning about this power. So power, it was not needed to mention this power, because this is not a hypothesis testing. So this is by mistake or maybe error which got overlooked. So this should not have been there. Now with this, I will show you how the author has calculated the sample size. So this is my assumption. You can see here, level of confidence 95%. Expected proportion was 49.6%, but for demonstration, I'll take it as 50%. Margin of error, that is the absolute, he has taken as 5%. And the finite population he has taken as 245. So I'll demonstrate it. Please see it carefully. So I will go to the Google, and we use statulator. So you type statulator and this, press this. So now this will come, and then you click this sample size. So the sample size, if you see this option of sample size here, and if you click on the drop down menu, it will show you two things, proportion and then mean. In proportion, you can see three options. Estimate a single proportion, compare to independent proportion, compare the paired proportion. In means also, it will show you estimate a single mean, compare two independent means, and compare paired differences. So can all of you see this? So now, because this involves only a single proportion, I will click this single proportion. So now you can see input value. So this interface is like this. Right now we are on calculator. So this level of confidence, if you keep this finger on this, it will also show this, what does this mean by the level of confidence, then this expected proportion, and then if you go scroll down, then you can see the margin of error. So this margin of error we have talked, like if you take the absolute margin of error in this case, so what is the level? The level of confidence was 95%. So I'll again show you this. Just see this. Level of confidence is 95%. Population correction 245. Finite population margin of error is 5%. That is absolute. And this 49.6 the author has taken from the previous study. So this 50%, this 49 point, this 95%, I have clicked this. Expected proportion, I will take 50 because 49.6 near round up. If you do, it will be 50%. And you can move this by like this. So this finger or this index finger, if you keep on moving, it will increase or decrease. You have to press the left button of your this thing mouse, and then right, or if you drag this right or left, it will be done. And then if you come here, this absolute value, you can see this 5%. This is the 5%. You can increase the value of this or decrease it. So, but now we have to calculate at the level of 5%. So 5% will be 0.05. And this is the absolute precision. So I will tell you about the relative precision also, but this is absolute precision. So what do I mean by this 5%? So all of you, please type in the chat box, what will be the range of value of this 50% if we take 5% as a precision? All of you. Yes, 45 to 55. You are right. So now you understand regarding the absolute precision. We'll talk of relative also. Now, is it clear to you? We talk only in terms of percentage point. We have not taken this 5% of 50. If I would have taken 5% of 50, that would have been a relative precision. But I am taking it as an absolute value, like 50 minus 5 and 50 plus 5. So it is 45 to 55. Now you press the calculate. Now, before I press calculate, you can calculate it. So the sample size is 385. Now you have to do the adjustment also, because the person has mentioned that there was a finite population correction of 245. So if you press this adjust, there's an adjustment for this finite population. You can put 245 here. There are two other options like clustering and response rate. But since this researcher has not adjusted his sample size for clustering and response rate, so we will not go. So we are giving you the examples which is already published in literature. So now press this update. So if you press this update, you can see a sample size of 150. Okay. And now if you see the write-up, so it is written that assuming that the 50% of the study subject in the population have the factor of interest. So this factor of interest, you have to replace it with the outcome. So what was your outcome? It was the percentage of cesarean delivery. So you will write, assuming that the 50% of the subject in the population have the cesarean section delivery and the finite population size of 245, the study would require a sample size of 150 for estimating the expected proportion with a 5% absolute precision and 95% confidence. So this will be the write-up. And now see what the author has mentioned. So if you see, the author is saying that the sample size was 359. You can see the write-up. No, sorry, the author is saying that minimum sample size of 150 patients. That is a typo error. So this is requiring 150 patients. Can you see this 150 patients? And in statulator also, if you see, what is the sample size? It is 150. So now you can see and you can check also. So whenever you get to know about a sample size, or you also review many articles, then please see their assumptions and check it once. So this was regarding one example. So now coming to another example. This is a second example. Factors associated with the development of early childhood caries among Brazilian preschoolers. So the researcher objective, what was the research objective? That researcher has to assess the prevalence of early childhood caries in children and investigate and influence the socio-demographic variable. So here the selection unit was the healthcare unit. Now, what adjustment ideally the author should have been done in this case? All of you please type. If we talk about adjustment, and if the selection of the unit, the study subject is at the level of healthcare units, means maybe that childhood or the children, the author has selected, although you have not gone into the detailed methodology, but yes, it is a cluster because the unit of selection is at the level of healthcare unit. So that the concept of or the adjustment for this design effect will come. So now this was the write-up of the author in that article. So at 44.8% rate for caries in the deciduous dentition, and the author has given a reference. So you can see this 15. That means the author has reviewed the literature and he has seen that in the previous literature, this 44.8% prevalence was observed. And then he has used this 95% confidence interval. Ideally, it should have been 95% confidence level. And then he has written 5% standard error. So the ideal term should have been the 5%, this absolute precision. And then he has written a correction factor of 1.2 was applied. So ideally, this correction factor, all of us should write the design effect because it is a cluster. So the design effect of 1.2 was applied. So now let's see this, how to calculate. So I'll go to the this statulator. I have reset this, otherwise it will take the previous. So I have reset this. So now what was the level of confidence? So level of confidence was 95%. Expected proportion was 44.8%. So roughly I will take 45%. So I'll reduce this to 0.45. And the margin of error was 5%. So this was 5%. You press calculate. So it is giving you a sample size of 381, but we have to do the adjustment also. So you press on this adjustment, you click on this adjust for clustering. So if you press this adjust for clustering, two options are there in front of you. Either you can have this intra-class correlation coefficient and cluster size. If you click this, so likewise we talked, like if you have to give, you can give any value. This intra-class correlation coefficient, if that value you cannot find, you can give it a value of 0.2. And this cluster size, from each cluster, how many sample do you want to come? You want to have, you can increase or decrease this cluster size. But since in this case, the author has used this 1.2. What is the reason for that 1.2? He has not mentioned, but let's see. So we will use this example of design effect. So design effect by 2 is the design effect, default design effect in statulator, because I said it is the safest option. But since the author has used 1.2, so I will type this 1.2 design effect here. And then the author has not adjusted for this response rate or finite population. So I will just press this update. So if you press this update, you will see, now first see the write-up. So assuming that the 45% of the subject in the population have the factor of interest. So how you will write this? You will write that assuming that the 45% of the children has the caries in their deciduous teeth or non-deciduous, whatever was the research question, and the design effect of 1.2, the study would require, the study required a sample size of 457 for estimating the expected proportion with 5% absolute precision and 95% confidence. And then again, it gives you a cluster size also. This assumes that a cluster size of 5 with 92 cluster. But this is again author discretion, the number of clusters and the cluster size in each cluster. So this was the 2 demo. And now it's your time to do the exercise. So you can see the 450, the author has calculated 456. And if you see that statulator, we have also calculated somewhere around 457. So this was correct. So this what we have seen this. This is again the same thing. So I'm skipping this. Now it's the time for you to practice. So I will show one example here and I'll give you the assumption. You all have to open the statulator, give the input value, and you have to give the sample size here in the chat box. So the question is, the research question is factor associated with the non-adherence to diet and physical activities among Nepalese type 2 diabetes patients, a cross-section study. The selection unit was patients, and the person has to assess the proportion of non-adherence to the diet and physical activity among type 2 diabetes patients. So this is the assumption. Level of confidence 95%, prevalence of non-adherence to the diet and physical activity from the previous studies is 63%, and margin of error is 5%. So now all of you please calculate the sample size and you have to type in the chat box. So yes, it is 359. All of you are right. Now see the second, 359 is okay. Now see the second question. Prevalence of cesarean section in urban health facility and associated factors in Eastern Ethiopia, hospital-based cross-section study. Now, this is the assumption. 95% confidence level, expected proportion of cesarean section 50%. Now you can see the margin of error is 4%. It is not 5%. And response rate is 95%. What is the sample size? 601, 632. So you have to take the all 601 people, please, response rate, you have to adjust for response rate also. 30 more. Okay, so that's why this 601 will become 632. This you have to adjust for response rate, mind it. So the correct answer is again 632, 632, you are right. So now this is the, again, I think we can skip this question because this is again single proportion. But again, you can do this. Let's do this because there are few more adjustments. So self-medication, this was a research question. The correct answer is 630, 632 is correct answer. Self-medication with antibiotics for treatment of menstrual symptoms in Southwest Nigeria, a cross-section study. So the option is to determine the prevalence of self-medication with antibiotics for the treatment of menstrual symptoms among university women. And here the selection unit was university. So you have to apply the concept of design effect. So this is the assumption. So it is, I mean, you just have to put these input. So here the population size is 50,000, margin of error is 5%, expected proportion is 30%, and response rate is 95%. Design effect is 2. Now calculate the sample size. To calculate this simultaneously, I will also show. So 30%, you have to do the 3 adjustment, 50,000, 2, and 95%. So you can go to window tab. Again, I'll adjust this, reset this. So level of confidence is 95. This is 30%. So I've reduced this to 30. Then the margin of error is 5%. It is the absolute. So I have just kept it like this. In adjustment, I have to adjust it for the finite population. So the finite population correction is 50,000. So here I have adjusted for 50,000. For clustering, the design effect of 2 is there. So I have done that. And that response rate is 95%. So I will put this to 0.95. And then I will update this. And then I will press this calculate. So you can see the sample size is 675, 688, depending on, I think, design effect or all. You can see here, you can see the input. So assuming that the 30% in the population have the factor of interest, a population size of 50,000, design effect of 2, expected response rate of 95%, the study would require a sample size of 675 for estimating the expected population with the 5% absolute precision and 95% confidence. And this assumes as cluster size of 5, but this is up to you. You can change this cluster size and the number of cluster which you have to take. So I will start with the two proportion now. So now sample size calculation for 2 proportion. Here this is the formula, but we are not going into the detail of the formula. In this case also, you should have this as these 3 figures as a must, this thing. You should have, because obviously you will compare the cases which we saw, mortality, COVID mortality in males and females. So there were 2 proportions. So you should have an expected proportion in group 1, expected proportion in group 2, or you can have odds ratio in group 2, because in analytical cross-section study, generally we have an odds ratio. And then the desired power, we usually keep this power as 80% and level of significance at 5%. It's by mistake, we have written as 95%. We keep it level of significance at 5%. And then that is the alpha error. So this is a must thing. And then you have this alternate hypothesis. So it can be a one-sided or two-sided hypothesis, but we recommend you to have a two-sided hypothesis. A two-sided hypothesis means you say that the mortality in male can be higher or lower than female. This is a two-side. Or one-sided hypothesis, you can say that mortality will always be higher in male. So generally, we always take two-sided hypothesis. The only difference is with two-sided hypothesis, the calculated sample size is a bit higher as compared to the one-sided hypothesis. Then in group size means how many male and female, how many numbers you have to take. The design effect response rate is the same, which we have seen in the one proportion. And then in continuity correction, we will see, because for a categorical variable, we define this continuity, we are using the Z distribution. So the continuity correction for now, you always keep this option ticked. We are not going into the detail of why this continuity correction, but for binomial distribution, that means for mean and standard deviation, thing like that, we have a normal distribution. But for binomial distribution, we apply this continuity correction. But for all practical purposes, you should keep this option checked. So now we will see at the example. So this is one example when you have to compare the knowledge, attitude, and practice towards voluntary blood donation, comparing the health science and non-health science students. So they have taken two university, but the selection unit was student, and that's why they are comparing. The two groups are the non-health and the health sciences. So now let's see. So this was the author description. So the author has written that the sample size was calculated using the EpiInfo version 21 by considering a 23.6% of prevalence of blood donation, and then 95% confidence level, and then 80% power, and a risk ratio. He has written as a risk ratio. Ideally, it should have been odds ratio, because it is a cross-sectional study and you cannot have a risk ratio in a cross-sectional study. And then 1-to-1 ratio is there in this comparison group, means the non-health and health, they will take equal number of students in both the category. And then they have added a 5% non-response. That means they have taken response rate as a 95%. So now let's see the sample size calculation. So the sample size in this case, if I see, so it was 23.6%. So I will take it as 24%. So 24% was the, so let's go to the statulator. So I have reset this. Now I'll go to the sample size and I'll click on two independent proportion. So if you click on two independent proportion, you can see here that it tells you regarding the expected proportion in the reference group and expected proportion in the test group. So in this case, you have the reference proportion in the one group, that is a reference group, and that was 24%. So I will take it as 24. And then the second you can see here as this, if you click this, so it gives you the expected outcome proportion in the test group. So in the test group, you can see that this is measure of association. So if you click this measure of association, then if you click this drop down menu, so you can see there is a difference in proportion, or there is a relative risk and odds ratio. Relative risk is there because this two proportion we'll use the same concept in the cohort study also. But right now I will click this odds ratio, and the odds ratio for this was 1.5. So I have written 1.5. And then I will press this calculate. And now I will adjust this because it is saying that the response rate is 95%. So I will adjust this continuity correction. I said that you should always keep it checked. So I will keep it as 95%. And I will press this update. And then in this option, you can see that 80% power is there. You don't need to decrease or increase this power because the author is assuming the 80% power, 5% level of significance, and two-sided hypothesis and equal group sizes. So all these things I will leave as it is. and then I will update. So if I update, the sample size is 528. So the total sample size is 1048 in each group. Okay, so this was taking 1.5, but I think in the actual, it is the odds ratio is, I guess it is the 2. So yes, in this case, odds ratio is 2. So what I'll do, I'll again go to this tabulator and I'll increase this odds ratio to 2. And now I'll press calculate. So you can see 174 in each group. The response rate is 95%. So if you go and see this actual sample size, it is 177 in each group. So it was okay. So now it is your time to do that. See this question. So this is the title is the epidemiology of hookworm infection in the school age children, a comparative cross-section study. So it's a comparative cross-section. So you have 2 groups. So you have to identify the prevalence and determinants of hookworm infection in urban and rural school age children. So the selection unit is schools. Now, the author has written 90% power and 50% outcome in the exposed group, odds ratio 1.5, design effect of 1.8, and rural urban ratio of 2, and a 15% of non-response. Now, all of you, please calculate the sample size. I will display this slide. Expected proportion in the urban kid is 50. Odds ratio is 1.5 for rural kids. And right now you do it for the equal group size, then we'll increase that. 1:1. So all of you, please calculate this. So till the time you guys are doing it, continuity correction is basically, we do it for binomial distribution. So any continuity, if there is any proportion. So in this case, like expected proportion will be 50%. So the outcome, yes and no, that is the binomial proportion. So in case of a binomial proportion, we use this option of continuity correction. Okay, so right now for you people, only this much is there. We will discuss about this more in detail, but since 2 options are again left, single mean and 2 means. So 835, the correct answer is, so the correct answer is, let's see, 835. So you can see here the author has also written, I think he has written 2509, but in this case, because he has written 2:1, so that ratio of 2:1, if you add one more, this 835 is in each arm. Remember, 835, be careful, it will write 835 in each arm. So twice of that will be in rural. So 835 into 3 will be the actual sample size. Okay. So now sample size calculation for single mean, we will see it. So the single mean, the formula of single mean is similar like you have seen for the proportion. It is z square s square by d square. But again, we are not going into the detail of these formula because we will use the tabulator. So in that also, for single mean also, if you see the must be criteria, that is the level of confidence, expected standard deviation, that is important, and the margin of error or precision, the absolute one. And the other 3 things may be like population size, design effect, and t distribution adjustment. We'll see all these while we apply this command in the tabulator. So this population size and design effect, this t distribution is applicable when your sample size is less than 30. So above 30, this t distribution and z distribution becomes the same. But less than 30, this t distribution, we apply this t distribution. So I will come to this. So I think I will skip this because time is less. So this is again the same concept which you have seen with respect to this proportion. The same concept is applicable for the mean as well. Like if you can recall the previous example, the same example I have cited here, that if you select the 5 different samples or the 100 different samples from the same proportion, so your mean value, because here the upper and lower limit is this much. So the confidence level, what do I mean by confidence level? That I am 95% confident that the population proportion or the population mean, in this case I'm using the mean. So the mean systolic blood pressure will lie between 108 to 117. So this was the concept of confidence level. And then how to get the value of expected standard deviation. So many times you will have this expected standard deviation in your literature. While you are doing the literature review, it will have. But if you cannot find it, then what you can do, you can take the first thing is to have a thorough literature research. If you don't find it, then do a pilot study around 10 cases to have that expected SD. Even if you cannot find it, then what you do, if 95% range is available, then you can calculate the because plus minus 2 standard deviation contains the 95% value. So if you divide this difference by 4, then you can have this expected standard deviation. Like in this case, for example, if 95% confidence interval for blood sugar level of a patient is 80 to 120, then the standard deviation would be 120 minus 80 by 4. So you deduct the highest minus lowest level, that is your range, and then you divide that with 4, because we know that plus minus 2 standard deviation contains 95% values. So that 95% confidence interval, upper and lower value, minus it and divide it by 4, it will give you the confidence level. If you have margin lower or highest, lowest and highest, maximum minimum is available, then we know that 6 standard deviation plus minus 3 standard deviation contains your 99.9% of the values. So in that case, you can define, you can what you can do, the maximum minus minimum divided by 6, that will give you a standard deviation. So in this case, if the range of the systolic and diastolic blood pressure is 40 and 160, then you can have the expected SD of 160 minus 40 by 6. That will be the 20. And if you are estimating a sample size for using a Likert scale, like a Penn scale, then in that case, whatever will be the value of that Likert scale, because the minimum is 0. So here the minimum is 0 and the maximum is 10. So the standard deviation is 10 minus 0 divided by 6. So it will be your 1.66. So ideally, your standard deviation, you should try to see it in your existing literature. Do a pilot study and try to calculate standard deviation. Or if you have got either 95% value, you can divide it by 4. If you have got a range, maximum and minimum, you can divide it by 6. And if you have, Likert scale sort of thing, then you can divide the total number of Likert values divided by 6. And that will give you a standard deviation. So now let's do the calculation. So the research question is, what is the average hemoglobin level of pregnant female who had cesarean section at AIIMS Patna in 2020? The estimation of mean hemoglobin level. So this was the research objective, and the selection unit is the pregnant female. So how will I do it? So I have taken this assumption, 95% level of confidence, expected standard deviation is 5. This is, I have taken the value from the previous study, and then I have used the margin of precision as, or margin of error or precision as 2. So in this case, so I have taken this expected standard deviation is 5 and margin of error is 2. So I'll go here, I'll reset this. In this option of statulator, from this drop-down menu, click the estimate a single mean. And if you click this, so my assumption is 95% confidence level, expected standard deviation is 5, that I have taken from the previous literature, and the margin of error is 2. That means my range of hemoglobin will vary from 3 to 7. And then I don't have to do any adjustment. So I will press this calculate. So you can see that I will need a sample size of 28 to study my this thing. And you can see here that always a mean, if you enter the value of your variable as a mean, it will give you very less sample size as compared to proportion. Because if you enter the value as a proportion, definitely the sample size is larger. And if you enter the value as a this thing as a mean, the value will be, the sample size will be low. So the calculated sample size, again, the second question is mean HDL level. So I will skip this. This is a standard deviation and this is, precision. So now you can do one example. So what is the average birth weight of newborn in district XYZ? Selection unit is PHC. And in this case, in selection unit is PHC. So it is the, you can see the assumption, expected standard deviation is 200 because it was the 200, it is the 200 grams. It is the birth weight of newborn. So 200 grams, the margin of error is 30 and the design effect is 2. The level of confidence is 95%. So all of you please calculate the sample size and type in the chat box. $348. Okay, so it was, it is right. So now we'll see the option of this two means. So this is the formula for two means. For two means again, because it will be a hypothesis testing. So you need the mean in the reference group. You need the mean in the test group. You need the pool standard deviation. Now here the concept of pool standard deviation comes, and this figure you may need to calculate it manually, because either you can have this pool standard deviation in literature, but generally we have seen that in literature this pool standard deviation is not available. So that you need to do it, and how you do it we will show you, and then desired power and level of significance that you will know. And then again the alternate hypothesis is the one-sided or two-sided. We have discussed about this, so I'll directly. So the formula for this pool standard deviation is SD1 square plus SD2 square by 2 under root. That means you square both the standard deviation, add it and divide it by 1.44, because under root 2 is 1.44. We'll see this. So now do the calculation. This was one example, serum cytokine levels in patients with chronic low back pain due to herniated disc, analytical cross-section study. So here the selection unit was patients. And if you see this, in this study, just concentrate on that highlighted portion. So a difference of serum cytokine level of 4 picogram per ml between the healthy volunteer and patients with low backache was considered significant. And on the basis of other studies, we estimated within group standard deviation for serum cytokine as 3.5. And the power is 0.95 and alpha is 0.05. And the calculated sample size for this, he has calculated this as 20. So now let's see this. So this was the 4. If I see, so the difference was 4 picogram and the standard deviation is 3.5. So with these two value, I'll go, again, I'll reset this. And I have to use this sample size for 2 independent means. So since here, if you open this 2 independent mean, this input value, it will give either the expected means. In this case, you have to show, you have to have 2 different means. But in this case, I have this difference between the mean. So I will click this. So difference between the mean, in this case is 4.5. And the expected standard deviation is 3.5. And because there is no adjustment, so I'll press this calculate, and you can see that total of 20 is required, 10 in each group. So that's how the person has also written that he has taken total sample size of 20 patients. So this was regarding the 2 mean. Again, you can, this is the same which we have done. And then you can see this. So the effect of resilience and turnover intentions. of nurses burnt out, a finding from comparative cross-sectional study. So in this case, this is the percentage of emotional exhaustion score. So mean emotional exhaustion score in Australian nurses was 20. Mean emotional exhaustion score in Chinese nurses was 24. Standard deviation he has written, pooled was 10.5. Desired power was 80%, level of significance 5. Alternate hypothesis 2-sided, group size equal. Now you have to calculate the sample size for this. So this is the last the exercise which we are doing. After that, I think I will again explain one concept which we decided initially, and then we'll end it because we have already exceeded half an hour. Although few concepts are still left, but I think this 1.5 hour time is less for giving all the concepts. So that's why I had to rush. I'm sorry for that. Those of you who have not been able to keep the pace, maybe you can have the recorded lecture and you can see it afterwards also. So it was 109. So yes, 109. That's okay. So now I think we are ending our this thing session here. So I think I'll answer a few questions which was put up by the participants initially. I think there was one concept of what was the clinical insignificance. Okay. So like in a study, I think in 1989, there was one author who did a study and he has seen that, he was giving, like if you give any hypertensive, antihypertensive drug to a group of patients, you have got two groups. So in one group, the difference, if you have given one drug to one group and the other drug to the second group, and you have seen that the difference in the blood pressure is only 1 millimeter, the control, maybe the mean BP of one group is, mean systolic BP of one group is 120. And the mean systolic blood pressure of the other group is maybe 118. So there was a difference of only 2 millimeter with those two drugs. But now, because you have taken a large sample size, the statistical significance was very high, like it was 0.001. But do you think that you can recommend that you should take drug 2, which is causing 2 millimeter lower blood pressure, as compared to the drug 1, which was giving 120? So that we mean by the clinical significance. The clinician decide whether by changing the drug, if he's able to have a control of only 2 millimeter, is it justifiable or not? So that we understand by clinical significance. A clinician justifies what is the level of, like maybe it can happen with any of the research question, that you have some clinical significance, that in my case, at least I expect my patients to have this much of lowering. Okay, so that we understand by the clinical and statistical significance. Yes, and the second question was, yes, PPT will be shared by all the participants. And how to decide for M? So M was your cluster size. So again, that cluster size, you have to decide depending on the feasibility also. There is a range, larger number of cluster you take, more power you have with your sample size. Like if you take 4 cluster out of 35, if you have to do a sample, if your sample size is coming 200, total cluster is 34, and you have calculated only, you have taken out only 4 cluster and 50 in each cluster, definitely it will have a less power, because the more number of cluster you add, it has a more generalizability. So that's how it is said that you should have a balance between the number of clusters and the individual in each number of cluster. So that's how we decide. There is a criteria, there is a calculation of how many cluster and how many sample in each cluster. That we'll do in the randomized control trial, when we'll do the cluster randomized control trial. So there we will show you how to have a balance between the cluster size and number of clusters. Okay, so you should have a balance between the two. And then the third is how to this something obtained. What have you written?
For range.
Okay, range. So range, you can see in the previous published literature, they give the lowest and highest. So range of that range of confidence interval. So that is there. If you click on statistical this thing software, like maybe the chi-square or the mean, it gives you, if you click that confidence interval, that gives you the option. Otherwise, the formula, mean plus minus 2 standard error. But again, standard error, why you need to calculate? These days, we don't calculate it. It automatically comes wherever you are applying your software, whether you are using GEMOV, you are using SPSS, or whatever you are using. It gives the confidence interval. Okay. And I think rest of the questions we have written down, and we may take up those questions in the next session. So thank you to all of you. So next month will be again the second Tuesday of the next month. That will be the sample size calculation for the case control study. And we'll again revise these concepts, because, all these input are same, in this cohort case control and cross-sectional. So we will do this once again. Till the time, you keep on looking all those literature and try to solve using this tabulator and see by changing what the sample size increases or decreases. Once you do it, then only you will understanding. How many times I will repeat, nothing will go to your head if you don't do it on your own. Because the main aim of this webinar, that at the end of this webinar, at least you should feel confident in tackling this issue of sample size. So I hope this cross-sectional study design, this both analytical as well as descriptive, some take-home messages must be there in your brain once you leave this, and keep on practicing for the whole month. So from wherever you look up your cross-sectional study, try to see what the author has written and whether they have given the correct justification of sample size or not. Because we have found out many articles, they are writing something and the result is something else. So keep on checking those things. That will that will be a wonderful learning for all of you. So thank you to all of you, and thank you to Clarnet team also.
Thanks a lot, ma'am. Thanks a lot for the wonderful session. Hope the knowledge gained out of this webinar will be of great help to all our participants. I would also like to thank our HOD, Dr. CM Singh sir and Dr. Shamshad sir, without whose support this webinar would have not been possible. But not the least, I would like to thank all our wonderful participants for being attentive throughout the session. Thanks a lot, everyone. Hope to see you on our next webinar. In order to get the registration link for the next webinar, kindly follow us at our Instagram page, meritindia.com, and we'll be sharing the link of our next session soon in our Instagram page. Thank you so much. We are